So for question 7, we have a bonnet that's represented by the rod AB, hinged freely at point A. The bonnet is of mass 12 kg and the weight acts through the points G at the midpoint. So what is missing from the diagram that have been given in the question is the weight itself. So we do have the weight. Weight is actually 12 kg multiplied by 9.81. Okay. And then for part 1, we need to calculate the value of the vertical force F that will just maintain the position of the bonnet. So of course, to maintain the position means net force must be 0 and also that the net moment must be 0. And for this question, given the hint that it is hinged freely at A, therefore it is more likely than not that we need to use moment to solve. So let's attempt using moment first. So the torque net should be 0, okay, to maintain equilibrium. And I've also mentioned in lecture before, for such question in the presentation, we must clearly state which point we are taking as pivot. So therefore, we will state it. So take point A as the pivot. And then using point A as the pivot, force F will be the one that provides for the clockwise moment. The weight will be the one that provides for the anti-clockwise moment. And to find moment, we will therefore need the length. The perpendicular distance of each force to the pivot itself will be, let us extend the line of action of F, and this will be the perpendicular distance of F to A, and then for the weight to A, this will be the perpendicular distance. But in order to represent the perpendicular distance, we will need the length of the whole bonnet. So let's call that L, okay? And then we also do not know the angle. Let's call it theta then, okay? But it is not important to actually solve for L and theta because once I start calculating the pivot, both L and theta can be cancelled off, okay? So therefore, let's call this x1 and let's call this x2. So to find the clockwise moment provided by F, so it is essentially F multiplied by x1, and then the anti-clockwise moment provided by the weight, so it will be 12 times 9.81, multiplied by x2. And x1 is the horizontal component of the length L, so F L cosine theta will be equals to 12 times 9.81. x2 is the point G to A, the horizontal component of GA, and GA is basically half of L, so that will give me half L cosine theta. Okay, and then by this point in time, you should see that L cosine theta, even though it's an unknown, I can cancel them away. So calculating, I get F equals to half times 12 times 9.81, giving me the final answer to be 58.9 Newton. Okay, and then part 2, we need to explain why it is easier to raise the bonnet by applying the force F prime in the direction shown than applying the force F. So essentially, okay, to raise the bonnet, okay, in this case, it must be a rotational motion about the hinge at A. So we are all just going to focus at using moment to think about this. And the easier way to raise the bonnet, therefore, should be the way to maximize moment. Okay, maximize moment with the minimum force required. So in this case, since the weight is a constant, and then the distance from the weight to point A at this instant in time must be x2 or equals to half L cosine theta as mentioned just now. To raise the bonnet, all I need to do is to make sure that my clockwise moment is slightly greater than half L cosine theta multiplied by the weight 12 times 9.81. Okay, I can do so by applying a force F or applying a force F prime. So the key difference is, okay, F, to provide that moment, I'm multiplying the perpendicular distance of x1, okay? But F prime would actually be a little bit more efficient than F, and the key reason is because for the same moment to be overcome, I am maximizing the perpendicular distance in this case. L is the hypotenuse, it must be greater than x1. So to achieve the same amount of moment required, which is basically just more than half L cosine theta 12 times 9.81, the anti-clockwise moment provided, okay, the anti-clockwise moment provided by the weight. Therefore, with a larger L, I can have a smaller F prime because the clockwise moment essentially is just F prime multiplied by L. So the larger the distance, the smaller the force required. So therefore, for part 2, why it is easier to apply the force F prime is really because the perpendicular distance of the line of action of F prime from A is larger than that of F, and therefore the anticlockwise moment provided by the weight being constant, F prime can be less than F itself. So let me show you the typewritten solution. So this is the typewritten solution, just like what I've recited just now. Since the perpendicular distance of the line of action of F prime for A is larger than that of F, and the anticlockwise moment due to the weight is constant being equals to W multiplied by half L cosine theta. Okay, thus F prime will be less than F itself. So for B part 1, we have a ship with a cross-sectional area A that's floating in the sea. So floating tells me that the upthrust should be equal to the weight of the ship. And in the first case, there are some cargo. So the initial upthrust must be equal to the weight of the ship plus the cargo. So we have the ship itself. We have the cargo within the ship. And then it was submerged underwater by a vertical distance of Z. After I unload the cargo, it rises by a vertical distance y. So therefore, to draw the second scenario, after the ship unloads the cargo, it has risen or rose by a vertical distance y, and therefore the the vertical distance that is still submerged is basically z minus y. So in both cases, the ship must be floating. So I have an upthrust one that should be equal to the weight of the ship plus cargo. And then in the second scenario, there is only remaining weight of the ship. And then I have upthrust 2 that should be equal to the weight of the ship. So for B part 1, I'm required to find the weight of the cargo, which is essentially the initial weight of the ship plus cargo minus the weight of the ship itself, which can be found. Okay, which can be found by using U1 minus U2. So therefore, the weight of the cargo is essentially U1 minus U2. And then we understand upthrust as V rho G, V being the volume that has been submerged, multiplied by density of the fluid, multiplied by G itself. So in the first case, upthrust 1, the volume submerged must be cross-sectional areas A multiplied by Z. So to find the full upthrust, it will be the density of the water, the seawater multiplied by G, minus upthrust 2, which is basically AZ minus Y. AZ minus Y multiplied by the density of the seawater multiplied by G. So after you multiply into the fraction and then simplify the whole equation, you should be able to get the final answer as AY density of the water multiplied by G. So the other way you can think about it is really the weight of the cargo should be equal to the upthrust that is no longer displaced by the volume. Okay, so because the cargo, after releasing it, the ship rose by a distance of y. Okay, so this amount of water is no longer displaced by the cargo itself. So all we need to find the weight of the cargo should also be equal to the weight of the water that is no longer displaced by the ship. So you should be able to get the final answer as the same. Okay, AY rho W times G. And then for B part 2, we are required to find the final upthrust. So the final upthrust is essentially given by the volume that is submerged finally, which is basically A Z minus Y multiplied by density of the seawater multiplied by G. And this will give you the final answer for part 2. So that's all for the topical quiz. So I'll see you again next time.